All right, guys, welcome back to this class. Now, again, I wanted to put this on record so that for students who are not attending it but who wants to see the video, at least they will still get this information from this video. So for the part 4A in the assignment, the latest assignment, if the so it says the alarm should be produced for exactly one sensor is on, and no, the alarm should not be produced when exactly one sensor is on. For two sensors and above, the alarm should be produced. Okay. So so the case is, okay, what about the case where I don't have any sensor on? So in that case, there should not be any alarm produced as well. Okay. All right. So let's see. Okay. So Thursday's lecture, I have yet to post it, so I'm going to post it today. And for the exam, I'm going to announce it on Blackboard. Again, I don't have the dates on the top of my head at this time, but it should be there on the Blackboard. Okay. All right. So let's get back to the class where we left behind. Okay. Just to give a quick recap of what we have done. Again, these are important concepts, design approaches that we encountered in the last class, that we introduced in the last class, right? So we looked at the design of a binary adder. Okay. Now we quickly realized that if I want to design a binary adder using the fundamental gate level, that's not very practical approach. Okay. I wanted to get a better approach for designing such complex circuits, right? And that's where we introduced the concept of modularity in design. You would design starting with small modules at the gate level, and you use those modules to build more complex systems. Okay, and towards that, what we've done is we examined the process of addition itself, the technique of addition. How do you do the addition process on paper, right? And we observed that the thing that we do at every bit, the addition at every bit position, is exactly the same. So all I have to do then is to create a module that can perform a single bit addition, taking into account the previous carry, producing a sum and a carry out. And all I have to do is just replicate that module, just copy and paste that module. Once I produce that module, copy and paste it, and cascade it like what we have done yesterday in the last class, right? And you get this n-bit adder circuit. Okay. And in the last class, we also looked at how do we transform this adder circuit into a subtractor. So here we actually utilize the two's complement subtraction to our advantage here. Okay, and we converted an adder into a subtractor by basically inverting the bits applied to the to one of the inputs and adding 1 at the Cn of the first adder, the first single bit adder. You converted that adder into a subtractor. Okay, and finally we also looked at the redundancy, right? We wanted to reduce the redundancies. That means I want to make as much as possible when I'm designing these systems, hardware, I want to make my systems to be multifunctional, if you will. Okay. Now, in other words, I don't want to have a separate adder circuit because again that takes space on my disk, right? On my when I'm trying to fabricate this as a chip, that's going to take space on my chip. That's going to consume power, right? So I would like to see if I can apply the same piece of hardware for addition as well as subtraction operations. And if I want to do that, that means I need to have some way of telling that piece of hardware what I want that hardware to do at a given instance of time, right? And we introduce the concept of control unit or control input, right? Where we will use the control input to specify at a given instant of time that can be programmatically controlled, as in you write a program at the high level, and when you write a minus b operation, then you are applying some input on the control input. The hardware applies some input on the control input to specify the adder, how it should be configured. And likewise, if I'm doing a addition operation, then a different input has to be applied on the control input to specify the hardware, how that should be controlled. Okay. So we introduced the concept of control inputs in our systems. Okay. And the way we have configured a adder circuit into an adder slash subtractor circuit is we use the concept of, this XOR gate, right? So we have the XOR gate, and if I have one of the input as the control input, yeah, I know, I don't know why that's doing that, but I can see that as well, the screen blinking. I hope it's not too much of a distraction. Okay, so you have the control input, you have the output, and from the perspective of the control input and the output, if I look at the, let's say, input A applied to this XOR gate, we basically exploited this phenomena, right? So you have this XOR gate. Depending on the control input applied as one of the input to the XOR gate, my F as a function of A is basically, F is equal to A every time I apply control input of 0, right? Whereas F equal to A prime when the control input was 1. This is what we have observed from the truth table of the XOR gate. So as far as if I fix the control input to be a specific value, my F and A, the relationship between F and A are related in this manner. And I utilize this in my design to build my adder slash subtractor circuit. So instead of directly inverting my B's, I would pass them through an XOR gate where the other input to the XOR gate is a control input. And the control input is connected to my C in. And so if I want to add, I apply a control voltage of 0 on my control input. And my B's just goes in as B's without getting inverted. So I'm configuring my circuit as an adder circuit in that instance. A gets added to B, and I get the sum. Whereas if I can have a control input of 1, if I apply control input of 1 on my control input, then my B's are inverted, right? And I'm applying a 1 on my C in. That means I'm adding A to the 2's complement of B, and which is nothing but A minus B operation. So that's how we have come up with the concept of an adder slash subtractor circuit that can perform both addition and subtraction operations depending on what you apply on the control input. So we introduced a new input to the system called the control input. Okay. All right, so that was about the binary adders. And towards the end of last class, if I want to design an actual hardware, okay, like for example a calculator, we want to do that using decimal systems, right? We want to, because we are familiar with decimal systems, I want to make a calculator that can add decimal numbers together, right? And when I say decimal numbers, as we discussed in the last class, we want to convert at the hardware level. In my digital design or the hardware itself, I'm dealing with binary numbers, and so decimal digits are basically converted into their corresponding binary coded decimal values, right? And now, so when I'm pressing my inputs on my, what is it called, on my keypad that consists of numbers, right, decimal numbers, what's happening at the hardware are, so you have to have some kind of a encoder that would encode each of my decimal digits into a binary code, right? So that encodes that into a binary code, into a BCD, or in other words, a binary coded decimal value, okay? And then I work with those binary coded decimal values as long as I'm in the hardware. And then when it's time to display the answer, I would use some kind of a decoder, like the 7-segment display decoder, along with the 7-segment displays to display the result as decimal numbers, right? So for a lame user, it appears as if you're already all working with just decimal systems. Okay? But of course, we know exactly what's happening. Everything is in binary, but then we are making them appear as decimal numbers and so on. Okay. All right. Now, in the design of decimal systems or decimal adders, all right. Again, I'm trying to design a single digit. Again, we are going back to the modular design approach when I'm trying to add an n-digit decimal number. we have seen that the addition operation at every individual digit position is exactly the same. You're adding two digits together along with the previous carry. You're getting a sum, in this case a decimal sum, and a carry out. Okay. Now, when I'm adding two numbers in any number system, two digits in any number systems, okay, the carry out is always going to be either 0 or 1. So I'm not too worried about that. Okay. All right. So I'm trying to design this module that can perform a single digit decimal addition. Okay. And this is what we have seen. So that's again, that's the digit 1. Trying to add that to digit 2. Again, these are decimal digits coming from my keypad along with the previous carry, because I'm trying to design a module that can perform this addition between AI and BIs. So let's say this is AI, some position BI, CI can, because CI can be 0 and 1, I can as easily just place it as is. AI, on the other hand, is encoded as a 4-bit binary code. So I would have this as, AI3, AI2, AI1, AI0, and then BIs could be BI3. So this is my corresponding binary coded decimal value of this AI, BI3, BI2, BI1, BI0. Okay, I'm trying to add these two numbers together. Along with the CI and getting a sum, a carry out, C out, which is a single bit, so I can easily just directly write that. And a sum, a decimal sum, that's important. A decimal sum SI, again, the sum that I directly get from this adder is in terms of binary coded decimal sum. So that means I have to have 4 outputs, right? Corresponding to each digit, I have 4 outputs. So that will be SI3, SI1, SI2, SI0. So this is the level 0 diagram of my binary coded decimal adder, or a decimal adder. Okay, let me actually write that down. So that's my level 0 diagram of my BCD adder module. Or in fact, this is a single digit. So if you're designing an n digit, that means you have to have n of those modules. That's what I'm going to design. And again, remember that that's the single module I'm going to design. I already see that I have 9 inputs, and I don't really worry about the outputs, but I have 9 inputs. So if I were to design it with fundamental gates, that's going to be complicated, right? Again, I'm looking at 2 power 9 cell K map, and not a very practical approach doing that. Okay. But how about doing alternate ways? Like how about the fact that when what I'm really doing here, right? If I take 2 examples, we have looked at the examples in the last class. When I add 2 decimal digits together, let's say 7 and 2, I get some answer 9. Okay, the corresponding binary coded decimal values for these is 0, 1, 1, 1, 0, 0, 1, 0. I add them together. When I say add them together, you can think about these being applied to a already built 4-bit binary adder. Now you already know from last class, how can we build a 4-bit binary adder? Yeah, I can build a 4-bit binary adder, and I can add these two 4-bit binary numbers using that adder. Okay, and what I get? So I have 1 plus 1 is 0, 1 plus 1 is 0, 1. And in this case, my decimal sum, this is my decimal sum. I'll call this the 4-bit binary sum. This is a 4-bit binary sum. These are equal, right? So that's good. What that means is I may be able to get by, instead of designing an entirely new adder that's specific to a binary coded decimal system addition operation. I may be able to get by using existing 4-bit binary adders, because all I'm doing here is really adding two 4-bit binary numbers together to get the sum. And in this case, in this particular example, it looks like the decimal sum is equal to the binary sum. Now, unfortunately, that's not true for all the cases. All right, let's take an example. Now, what happens when I add, for example, 7 plus 3? My decimal sum should read, the correct decimal sum should read 10, right? In other words, my 1 in this case is a carry out. This is a carry out. And this is the decimal, then this is the actual sum. So 1 is the carry out, 0 is the sum. Okay. Now, if I do this corresponding operation using a 4-bit binary adder, what am I going to get? So again, 7 will be encoded as 0, 1, 1, 1. 3 would be encoded as 0, 0, 1, 1. I add them together. That means when I'm applying these as inputs to my binary adder, for a 4-bit binary adder, it would assume that these are binary digits, adds them, gives you the answer. So the 4-bit binary sum, so whatever sum I'm going to get here is the 4-bit binary sum. And what am I going to get here? 1 plus 1 is 1, 0. That's 1, 1, 1, 0. That's it. So that's 1, 0, 1, 0, which is the right binary sum. There is nothing wrong about that. The adder works fine. However, this is not the format that I need. This is the 4-bit binary sum. That's the format I need for my decimal sum. That means for my decimal sum, the correct sum should have read 1 as the cout, okay, and zeros for my sum, right? 1 as the cout, 0 as my sum. So that's in decimal. That would have been the right binary coded decimal sum. So for some instances, looks like my decimal sum is equal to the binary sum. And in some instances, like this, for example, in this case, looks like my decimal sum is not equal to the binary sum. So that means I need to do something to correct for that. Okay. All right. Are you with me until this point? Are there any questions? Because again, this is going to be a little bit more involved than what we have seen in the last class for the binary adder. The binary adder was a little bit more direct. In here, we have to really think modularly, first of all, using existing modules, and then the design itself is going to be multi-staged. Okay, so make sure that you're following every step properly. So if you have any questions, this is a good time to stop and ask me if you have any questions on this so far. Okay, no questions? Fine. All right, so let's move on. So that's the observation. So it's correct for some time, for some instances. For other instances, it doesn't look like the binary sum and the decimal sum match. Okay, so let's examine this in a little bit more detail and see what we can do about this. Under what circumstances do I get my binary sum to be equal to the decimal sum? And under what circumstances my binary sum is not equal to the decimal sum? Okay, let's look at this. All right, now let's do 6 plus 3. It's 9. Let me see. Okay, let me put it this way. Let's say my binary sum. Let's compare between the binary sum and the binary coded decimal sum. Let's compare between these two sums, binary coded decimal sum. All right. Binary sum of 0, C out, and then that's the sum. That's my C out. Let me actually put that down. C out, S3, S2, S1, S0. Then let me call that something else. Let me call that K out. Just to distinguish between these binary sum and decimal sum, let me put these stars on as my S's. Here I have S3, S2, S1, S0. Okay. Binary sum of 0, 0 plus 0 is 0. By my BCD sum should be the same, right? There is no difference. A binary sum of 1, 0 plus 1. I get it? A binary sum of 1 would be 0, 0, 0, 1. BCD sum would be the same thing, right? 0, 0, 0, 0, 1. What about 1 plus 1? 1 plus 1 is 2. That's my decimal sum. And my binary sum would be 0, 0, 0, 1, 0, 0, 0, 1. I'm adding these together. 1 plus 1 is 0, 1. That's my binary sum, which is the same as my decimal sum. No worries there. So 0, 0, 0, 1, 0, 0, 0, 0, 1, 0. Perfect. Nothing wrong there. Okay. And so on. What about 9? 0, 0. The binary sum of 9 would be 1, 0, 0, 1. How would you get 9? Let's say 6 plus 3 is 9. I'm adding 2 decimal digits, 6 plus 3. I get 9. Corresponding binary coded decimal values would be 0, 1, 1, 0, 0, 0, 1, 1. And I get a binary sum of 9. These two are in the right format, or this number is in the right format. I don't have to worry about that. So my BCD sum is also the same. Okay. What about 11? 11, which I can get by adding 6 plus 4. I get 11. I'm sorry, 6 plus 5. Yeah, okay, 6 plus 10. Let's do 11. 6 plus 5. I get 11. That's my decimal sum. When I'm doing the corresponding addition operation in binary, that will correspond to 0, 0, 0, 1, 1, 0. Adding that to 0, 1, 0, 1. I get, what do I get? 1, 0, 1, 1. So that's my binary sum, 1, 0, 1, 1. And the correct way of representing that as a BCD sum would have been 1 in the carryout, and this one expressed as a 4-bit number, binary number. So the correct sum, so if the binary sum was 1, 0, 1, 1, the correct binary coded decimal sum should have been 1 in my carryout, 0, 0, 0, 1. Likewise, 10 should have been 1 in my carryout, 0, 0, 0, 0. All right? Do you see that pattern now? As long as my sum between the digits sum between the decimal digits or binary coded decimal digits, call that same thing, values is less than or equal to 9 implies my binary sum is in the right format. My binary sum is equal to my binary coded decimal sum. We have seen that. This is my decimal sum. That's the binary sum, and that's 9. That's 9. right, in the right format. Perfect. It changes now when my BCD sum is larger than 9, then my binary sum is not equal to BCD sum, or at least it's not in the right format. The sum value itself is right. The binary sum value itself is right. This is 11, but it's not in the right format. The right format would have should have been C out of 1 or K out of 1 followed by 1, right? Okay. So what should we do? What should we do to correct for that? Obviously, as long as the sum is less than 9, I don't have to do anything. Those two sums match. The only correction I have to apply is when the sum exceeds 9. Yeah, Sam.
If we add 6 to
Okay.
the binary sum.
6 to the binary sum. Okay. That's a good thought. Could you elaborate why you would like to add 6?
So if we go through all the digits, the 4-bit digits 0 through 15, if you add 6, in case for the 6 plus 5, it would give us a carry out of 1 and then 0, 0, 0, 1.
Yeah, perfect. Yes, that's absolutely right. So the correction factor that I have to apply is 6. Why 6? Again, if you notice, if I start writing my decimal numbers, right, decimal sums, that goes as 0, 1, 2, 3, so on, 9. Until 9, I don't have a C out. I don't have to produce a C out. However, after 9, I need to produce a C out of 1, 10. So I need to start using 2 digits, right? In the case of binary numbers, I start with, let's say, 0, 0, 0, binary sums, 0, 0, 0, 1, so on. 15 would be, okay, let me just take this out. So on. 15 would be 1, 1, 1, 1. I will start producing carry out for the binary number, 4-bit binary number. I start producing a carry out only after 15, right? So this is 15. So if I want to write 16, then I will use the carry out of 1 and followed by zeros. So 9 for decimals, I need to start producing a carry out after 9. For binary, I need to start producing a carry out after 15. So that means there's a difference of 6 between decimals and binary. 15 minus 9 is 6. So if I add a factor of 6 to my binary sum, every time it exceeds 9, then I will produce the right BCD sum. Right? Just as an example, 5 plus 9 is 14. 1, 4. Again, expressed as binary coded decimal values, that would be 0, 1, 0, 1. 9 would be 1, 0, 0, 1. I add them together, I get 1 plus 1 is 0, 1, 1, 1, 1. That's 14. That's the right binary value, but it's not in the right BCD format. How do I change? Obviously, I need to produce a carryout. And as we discussed, the difference between the decimal and the binary sum is a factor of 9, a factor of 6. If I add that factor of 6, 0, 1, 1, 0, I would be extending the binary sum so that I get the right BCD sum. So in this case, that will be 0. 1 plus 1 is 0, 1. 1 plus 1 plus 1 is 1. 1. 1 plus 1 is 0, 1. So that's the carryout of 1, and that is 4. So every time my binary sum exceeds 9, I have to add 6 to that binary sum to make it into the right BCD value. Okay. All right, so let me put that down here. As long as the sum between the BCD values are less than or equal to 9, I don't have to do anything. Less than or equal to 9, I don't have a carry out, and then the numbers match. However, when the BCD sum is larger than 9, I start producing a carry out, and my binary sum is not equal to BCD sum. So the right BCD sum can be obtained. BCD sum in this case will be, the right BCD sum will be binary sum. Okay. Plus 0, 1, 1, 0, 6. We add a factor of 6 to the binary sum to get the right BCD sum only under this condition. Otherwise, I don't have to do anything. As long as the sum is less than or equal to 9, I don't have to do anything. Only when the sum is larger than 9, I have to get the right BCD sum from my adder. I take the binary sum from my adder and add to that 6, and I get the right BCD value. Okay, this is important. I hope you get this. If you have any questions on this part, this is a point you would stop me and ask me if you need any clarifications on that part, because that we will base our design based on this now, based on these statements. Okay, any questions so far in this? Are you with me until this point? Okay, very good. Good. Let's move forward then. All right, so now my design boils down to, let me see if this makes sense. So let me take this out. So what I'm going to do now to simplify my design is I will start using, number one, use existing. You know already how to design or design your own 4-bit adders. Use existing 4-bit adders, 4-bit binary adders, to perform, instead of designing everything from the scratch, to perform BCD operations, BCD addition operation in this case. What that means is I will take okay, so that's a 4-bit binary adder to which I'm applying my BCD values. Okay, so that's your A3, A2, A1, A0, B3, B2, B1, B0, along with the Cin from the previous, because ultimately you want to design the full adder, right? So that's your Cin. So that's the first binary coded decimal value applied. That's the second one. That's your Cin from the previous bit, from the previous digit addition. Okay, call them BCD1, BCD2, and then I'm getting the C out. That's your C out, and the sum S3, S2, S1, S0. Now remember that this sum that you're directly getting from the binary adder is the binary sum. May not be the right BCD sum. It's the binary sum. And now I need to check if the sum is larger than 9. Right? I need to design a circuit that can take these as inputs, S0, S3, S2, S1, S0 as my inputs. Let me call this S3 star, S2 star, just to distinguish between the actual sum that we need and the sum with that. Okay. All right. and that's my C out. Okay. I need to check, first of all, if so I need to design some kind of a logic circuit here that takes in these values, the sum values, 5 inputs. Okay, this is something that you need to design. So this is something that you need to design, and producing me a value k0, for example, such that I need to design this unit such that my k0 is 1 every time my sum from this adder is larger than 9. Right? Okay, let me repeat this. I'm trying to design this logic decision circuit, if you will, or decision circuitry that would tell me when my sum is larger than 9. When my sum is, so that means I will specify the design for this adder such that, for this particular unit such that k0 should be 1 every time the sum from this binary adder, every time I C out S3 star, S1 star, S2 star, S1 star, S0 star. The value of that is larger than 9. And that should be equal to 0 if, again, the sum is less than or equal to 9. That's how my circuit should behave. Whatever I'm going to design should basically look at these values, the sum that I'm going to get directly from the adder, from the binary adder, examine the sum to see if it's larger than or equal to 9, or if it's less than or equal to 9. If it's less than or equal to 9, I define an output k0 such that the k0 is 0 every time the sum is less than or equal to 9. K0 is 1 every time the sum is larger than or equal to 9. Because once I get this, now I know exactly when to add 6 to this sum, right? Once I know this, I can basically tell my circuit when to add 6 to my binary sum. Okay. All right. So let's design this first. Design this simple unit first, and then see how we can actually utilize that to design my entire binary coded decimal adder. Okay. So let's do that. All right. So now we exactly know this is my level 0 diagram. I know what the inputs are to this system. I have 5 inputs, 1 output. Okay. I have 5 inputs, so these are my inputs. Those are the outputs. And let's look at the truth table for that and start designing the system. Okay. So let me get rid of that for now, and then we'll draw this again. Okay. So let me properly do this now. So again, the system takes in C outs S3 star, S2 star, S1 star, S0 star. Okay, we don't need these now. And looks at K out, right? So as long as my sum is less than 9, so that's 0, 1, 0, 0, 1, that's 9. And that's still 0. Okay. The moment the sum is larger than 9, which is 10, which is 1, 0, 1, 0, again that's the binary sum, then K out should be 1, indicating that the sum is larger than 9. Right? Now, by the way, what is the largest sum I can get here? Remember, we are trying to add two BCD numbers together, BCD values, plus the C in from the previous bit. So what is the largest possible sum you can get? When you're trying to add two decimal numbers together, two decimal digits together, along with the previous carry. Largest possible sum. like you're adding 2 decimal digits together, right? 19. That's it. Because my largest decimal digit is 9. I'm adding 9 to 9 along with the previous carry 1. That's the largest possible sum I can get, which is 19. I cannot get a larger sum than this. Something to keep in mind. All right. So that's 10. 11 would be 1, 0, 1, 1. That's 1. 12 would be 1, 1, 0, 0. Still 1 for K out. 13 would be 0, 1, 1, 0, 1. 14, 1, 1, 0. 15, 1, 1, 1, 1. 16 would be 1, 0, 0, 0, 0. 17, 1, 0, 0, 0, 1. 18, 1, 0, 0, 1, 0. And 19, 1, 0, 0, 1, 1. Okay, out is a 1. And 20 would be 1, 0. And I'm trying to list out all possible combinations. So that's 1, 0, 1, 0, 0. What should be my K out? I'm designing a system for K out. I don't have a sum called 20. When I'm adding 2 decimal numbers along with the previous carry, I cannot generate a sum larger than 19. So that's going to be my don't cares. Okay, all the way down to 1, 1, 1, 1, 1, which is 30. What is 31? Right? So all don't cares. Okay. So again, my circuit should take an input, the binary sum, which consists of 5 inputs: C out, S3 star, S2 star, S1 star, S0 star, providing me with an output that is true when my sum exceeds 9. That's 9. Starting with 10 until 19. Those are possible values for my binary coded decimal sums exceeding 9. So for those values, I have 1s for my K out. And for the rest of them, starting with 20 to 31, I don't have those sums. When I'm adding 2 decimal digits together, I'm not going to get those sums anyway. So these are all don't cares. Now I need to design what K out is. Now I could do 5 input K map. I don't want to do that. Let me see if I can do it just through logic. Okay. I can see that my K out is 1, definitely 1, when my C out is 1. Right? Do you see this? As long as my C out is 1, my K out is 1. That means my K out, if I want to write this, my K out is 1 if my C out is 1, or because it's also 1 for other cases here. Because here my C out is 0, but yet my K out is 1. I need to see what other combinations would I be getting for which my K out is 1. Okay. So my K out is 1 in terms, so I can write the K out as C out, or now I need to look at dependency on S3 star, S2 star, S1 star, S0 star, which boils down to like a 4 input K map. I looked at the dependency for C out already, so that's taken care of. So I don't have to worry about that. K out is 1, if C out is 1. Now, in terms of S3 star, S2 star, S1 star, S0 star, I'll draw the K map between them and K out, and obtain the relation. Okay, let's see what we get. Are you following me with this? How we have through logic trying to simplify this. So that's S3 star.
Yes.
Okay, thank you. S1 star, S0 star, 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0. Okay, 0, 1, 2, 3, 4, 5, 6, 7, 9, 10, 11, 12, 13, 14, 15. And starting with what? This is 10. through 15, that should be a 1, right? 10 through 15, that should be a 1. So this is what I get for the K map. Combine them. All right. And my K out would be C out, or the product term corresponding to this combination is S3 star, S2 star. Product term corresponding to this combination is, I go down, that is S3 star. Go across, I get S1 star. So now I have a relationship for K out. I can design my K out, my system, the control logic, if you will, that would tell me when the sum is exceeding 9. Okay, every time, and then that will produce a 1 as the output. Okay. All right, let's get back to our design now. Now we know exactly what K out should look like in terms of S3 star, S2 star, S1 star, S0 star, and C out. And now let's actually finish the entire circuit design. Okay. Starting with, so first I'm trying to add the two binary coded decimal values. So that's a 4-bit binary adder. That's your A3. That's your first binary bit to be added, binary numbers to be added. That's your second binary numbers to be added. Although I'm applying my BCD values here, this is still a binary adder. And that's your C in. So that's my first binary coded decimal value being applied. The second binary coded decimal value being applied. Right? Remember that was AI3, AI2, AI1, AI0. That's what we started out with. BI3, BI2, BI1, BI0. That's your C in. Or in this case, that's your CI minus 1 that you're applying to that C in the C in position of the adder. And then you have, that's your C out, and S3, S2, S1, S0, which in this case we are calling them S3 star, S2 star, S1 star, S0 star. We are passing them through, and we call this C out. We are passing them through the control unit that we just designed. This is the control logic for that unit that would specify when my sum is larger than 9, and it outputs a value of 1 when it does that. So that's my control. It takes in these values, producing me a K out. Okay, K out. K out is 1 if sum is larger than 9, equal to 0 if sum less than or equal to 9, if this sum is less than or equal to 9. Now, I need to add a 6 every time my sum exceeds 9. So what I will do is, I'll use another binary adder, because I'm adding 6. How am I adding 6 as a binary number, right? So I'm taking this, adding that to 0, 1, 1, 0. That's 6. That's a 4-bit binary number I'm adding to this sum every time my sum exceeds 9. So I will use another binary adder here, which adds 6 to the, that's another, okay. All right. That's another 4-bit binary adder. Okay. And let's say that's your A3, A2, A1, A0. Then you have B3, B1, B2, B1, B0 positions for this particular adder. And of course, you have C in for this adder. I don't have to worry about C in here, so I just ground it for that particular adder because I just need to add 6 to that. and I'm applying my S3 stars or S stars as one of the input to my binary adder. Okay, so again, that's your S0 star, okay? I just don't want to mess this diagram. So basically that's coming from here. So here is that's connected to my A0, okay? Let me just to be consistent, let me actually redraw this nicely this time. So let's see out. All right, so this time, applying that here. That's my A2. Applying to A1, A0. Okay. So the sum is going to that additional 4-bit binary adder. I want to add 6 only when my sum exceeds 9. So what I will do here is, the way I will add 6 to that under these circumstances is, I will place this as 0, apply a value of 0, constant 0 value here, and then I take k out from here, apply this on B1 and B2. Okay. What does that mean? If my k0 is 0, which happens when my sum is less than or equal to 9, I'm taking this sum and adding that to 0, right? If k0 is 0, that means I'm adding that to 0, 0, 0, 0. So I'm not doing anything. So whatever the binary sum is coming out from here is going out as is, without being added, without being changed. On the other hand, if my sum does exceeds 9, as in this case, my k0 is 1, that means I'm adding this sum, the binary sum, to a value of 0, 1, 1, 0, which is 6, right? So I'm taking that, adding to 6, and I'm getting this sum. So this sum, the output of this particular adder is what we need, really. So that's so you'll have again C0 here, S3, S2, S1, S0. So that's the correct BCD sum. I'm going to ignore this. I don't need this. The K0 or the output carry for the decimal adder would be coming from this K0. So this K0 is what is going to be functioning as your K0. Okay. So that's a carry. That's the sum. Let me call this carry. So you have dual purpose for this K0. K0 can perform both as the control logic as well as as you can see here, right? Every time my sum exceeds 9, my K0 is 1. So that can function as a control logic here. Okay, as well as your output carry. And these are the sum values. These are the correct BCD sum values, which are my S3, S2, S1, S0. All right. So as I mentioned, it's a little bit more involved, a little bit more, with additional step. But if you understand this, the principle behind it, how we approached it, and practice this all by yourself, this should be more comfortable to you. And I would strongly recommend that you do it. Now hopefully, you kind of got it now, and then I would like you to go back and examine this in more detail. What are the steps we have taken to get to this stage? Okay, understand this, close your book, and then start designing it yourself. Once you're comfortable designing this, now you would work on the last problem of your homework, the 5A and B. 5A is pretty simple. The half adder part, you should be able to easily get it. The 5B is a little bit more complicated. Again, I would like you to go for the elegant solution. Okay, so what I would like you to do for the 5B is go and approach that using the modular approach. See if you can use existing modules. The hint is, see if you can use binary adders. You need to decide what size binary adder you need to use. In this case, for example, we have used a 4-bit binary adder. For part 5b, you should decide what size binary adder should you choose. Okay, and see if you can implement that circuit. And that's in part 5b, as you will see, is much more simpler than implementing a binary coded decimal adder. So attempt the problem, and apply the same principles while you're solving the problem 5b. Okay, it will be more fun doing that. Otherwise, you will have to deal with 5 input K-maps, and test becomes too messy, I would say. I would strongly recommend that you don't do that approach. I would strongly recommend that you do the modular approach that we just discussed. Okay, let me take a pause, give you some time to think over it, and see if you have any questions now. Any point that you need clarifications on, and then we can go back and then start examining it. Okay, Julia, do you have any questions? Does the approach make sense? Maybe she's not here, looks like. Okay. Kamran, what do you think? All right, looks like Kamran is not there too. I hope you guys are there on the other side of the screen. Okay, very good. Okay, very good. Good to see that. Good to, it's good to get some kind of feedback every now and then. Otherwise, it just feels like I'm talking to the screen. So I need to be ensured that there are some actual beings on the other side of the screen. All right, so very good. So it will take some time to digest it. So again, spend some time, go over this approach, and uh, just make it your own, by practicing it again and again. Now, on the second midterm, you will see a similar problem. Okay, I can tell you that. So one problem, if you get the approach right, then you have your 25 points right away, because I can guarantee you that there will be a question that will ask you to solve similar kind of problem, like your 5b. It could be, for example, instead of a tertiary adder, it could be a penta adder, like a base 5 adder. Okay. Again, it's not like I'm going to give you the base 5. I just giving you an example here. Okay, so just make sure you get this down properly. All right, and of course, if you don't still understand this, feel free to reach out to me, and then we can discuss this in more detail. All right, so that's good. So in this approach, we have chosen existing modules to design and make our life easier in the design process. Okay, again, still a modular approach. All right, so what we will do now is shift gears a little bit, okay, and examine some other aspects in the design of programmatic systems or programmable systems. Okay. Now, again, I'm sure each one of you must have worked on some kind of a programming language, even if it's even at the basic level. You must have done some kind of programming, I'm assuming, right? And most of the time, you want your program to perform certain operations, right? Why are we writing programs? Because we want to make our life easier. We want to make the computer work on some routine operations, okay? And for that, we write code. We write code in the form of, loops, right? Now, when we try to write loops, or when you're trying to write if-else statements, so these are the most common ways that we actually designate some decision making to the computer, right? That's how the computer takes decisions or makes decisions based on what we write in the if-else statements, based on what we write in the for loops and while loops, right? So every time these kind of codes execute at the hardware, when you're writing this codes at the hardware level, when these codes execute, what's really happening at the hardware level? How does the hardware and software communicate? That's one aspect. And then these particular, and then when you're writing these codes, what are the corresponding things or changes that are occurring at the hardware level? Okay, and how can the hardware be configured to enable these decision making aspects in the program? Okay, so let's talk about that briefly today. At least we get started on that, and then in the next class, of course, we will focus more on achieving decision making. Okay, so let's talk about decision making. Again, most of the time, your code on the high level code would read something like, for example, if you're checking for a condition, you got some condition here. If this condition is true, then you write a set of statements, right, that you want your uh, computer to perform for you. Some condition is true. Like the condition could be, for example, if you have two variables a and b, you have assigned some value to a and b. If a is larger than or equal to b, then you perform some operation. Else, again, that's your typical if-else statement, right? Or else, if a is less than or equal to b, or less than b, then you perform a different set of operations, or you write those codes for the computer to perform. So that's one aspect of decision making. You're delegating some of the decision making to the hardware, to the computer, right? Now the other instance is when you're doing for loops, for example. Again, you're writing a loop for I equals 1 to n. You write some statement that you want to repeat n number of times, and then you basically you increment I at the end of the code, and it checks for the value of I. If it's reached n, and then if it's not reached n, then it continues the execution of the code, then increments that, checks it back, and so on. So that's how the for loop executes, right? And likewise, you have the while loop, and so on. So these are the the programming constructs that you use to make decisions, to make your program more programmable, to make your instructions, your computer more programmable, right? Okay, now, so as you can see here, we are looking for conditions. Okay, now at the hardware level, when I write this code, what is happening at the hardware level? How are these codes being interpreted at the hardware level? What enables these decision making, right? And so let's actually see step by step what happens. Every time I'm checking for a condition, for example, let's take the example of comparing A larger than or equal to B. So basically, I'm trying to do a comparison operation here. Okay. So one thing I can do at the hardware level is, because we have already designed a subtractor, right? Every time I have to compare, what I will do is I perform an A minus B operation. Okay. I'll perform an A minus B operation, and if assuming that in this case Yeah, a minus b is larger than 0, okay, but that tells me that a is larger than b, right? If a minus b larger than 0 of the operation, that tells me that a is larger than b. Let's say if I'm checking for a condition, let's say if a equals b, then do certain operations, do these operations, these statements, or execute those statements. Now, again, because I'm trying to compare these two numbers, magnitude between these two numbers, at the hardware level, what I can do is, or what I can configure such that I can perform again a minus b operation and look for the sum bits. If the sum bits are all zeros, that means my a is equal to b, right? Now, so these are some of the ways that we can start thinking about, how we can actually utilize the hardware and configure it or enable it to perform this decision making at the hardware level. When I'm writing this code at the hardware level, what should I be doing? What should the hardware be checking for? Okay. Now, it turns out that if I want to do these comparisons, it will be much more simpler at the hardware level to work with what is called the concept of flags. Instead of trying to look for each bit to see if that's 0, or for example here, if a minus b is larger than 0, how do I check for this? How to check at the hardware level? How to check? How to check if the sum is larger than 0? Do I have to look at each individual bit and make a decision? Right? That's not a very practical approach. A better approach is to use the concept of flags to check for these conditions, or to check for these multiple conditions. Okay. So what are flags? I will define flag as a single bit indicator. Okay. So let me start describing what that flags are. A flag, I can have multiple flags. Okay. First of all, I would define this as a single bit indicator. Okay. Now, a single bit indicator that points to the result of an operation. That points to the result of an operation. In other words, if I want to check for this condition, for example, I will configure a flag called a 0 flag. Instead of checking for each individual bit to see if that's 0, I'll configure a flag, a single bit flag called a 0 flag, Z flag. Okay. And I will configure it, I will implement that flag at the hardware level such that my Z flag, single bit indicator, is true, okay, only when my sum, all the sum bits are zeros. That means if I do get an answer called 0, 0, 0, 0, 0, that should set the flag, the 0 flag. For any other value where all the bits are not 1, or all the bits are not 0, then the 0 flag should be false or 0. So now I don't have to look for, so if I configure 0 flag, I don't have to look for each individual bit. I can simply look at my Z flag. If my Z flag is 1, then this particular condition is satisfied and the code can execute. Whatever code you have written, that can execute. If the Z flag is not set, then of course this condition is not satisfied. I'll look for other condition, the other set of code will execute. Okay, but for any of these operations to work, I am still doing this operation first at the hardware level. For any of the comparison to work, I'm still comparing between A and B. I'm still doing A minus B operation first. And looking at the result, coming up with my flags. Okay. All right. So let me see if you have any questions here on the concept of flags. Of course, we have not implemented any flags. Ultimately, we have to implement these flags. But at this time, do you have any questions on what does that mean by flags? Are you with me at this point? Does that make sense? Okay. All right. So that's good. So from now on, we should always think about, relate your high level language code to what is correspondingly, at least at the intuitive level, what is happening at the hardware level down somewhere. So that's your high level language. That's at the hardware level. Okay. All right. Okay. So if you don't have any other questions, then I will see you guys on Thursday. Okay.
Have a nice day.
You too. Thank you, guys.